All right, so there's all of problem 3, and you notice that the dissociation that we calculated was 6.71%. So I remember in class I said something about if the percent dissociation is greater than 5, then we can't make the approximation. That is according to your book. Now, after talking to Dr. Payne, getting a little bit more insight, I realized that we still can use this approximation. This is still good, and I'm going to explain why exactly it is good, okay? So, and an easier way, instead of having to go through and calculate X, and then calculate the percent dissociation to see if it's okay, and then having to go back and do the quadratic formula. We're going to avoid all that, okay? And in order to do that, I need to explain to you the relationship between pH and pKa, which we have not yet talked about pKa, and then we're relating this to whether or not we can use approximations. So this is our 5th point as far as things that we must know. All right, so first things first. pH is related to the pKa. In fact, it's almost the same. Now remember the Ka is the acid ionization equilibrium constant. So now all we're doing is putting an operator in front, which is the P. Just like with the pH, the operator was the negative log. So this is like saying negative log of the H plus concentration, while this is similar to the negative log of the Ka, okay? So this is just what we're remembering. This is true. And then on top of that, the pOH is similar to the pKb, which is the equilibrium constant for ionization constant for the bases. All right. So similar thing, negative log of the OH minus concentration is very close to the negative log of the Kb. All right, so what exactly is all that? Well, we haven't talked about this thing called the Henderson-Hasselbalch equation, but I'm going to introduce it to you now. So we can make these assumptions because we're using the Henderson Hassel, all right, let's try that again. Hasselbalch equation. And this is found on page 599 in your textbook, and it's also in chapter 17. So I'm going easing in a little bit of chapter 17 as we're talking about chapter 16. Now, I know that you've talked about this relationship in lab because it came up on your practicum for some people. Hopefully I didn't give away any information. But anyway, so you guys have talked about this in lab and you've talked about buffers. So here's the background story behind it, okay? So the Henderson-Hasselbalch equation for pH is equal to the pKa plus the log of conjugate base, that's what this A minus is, conjugate base over acid. Okay? Now, similarly, the pOH is equal to the pKb plus the log of conjugate acid over base. So remember in the previous set of key concepts that I talked about, we talked about what was a conjugate acid and what was a conjugate base for acids and for bases. So when we have an acid, the conjugate acid is the anion, and the acid, the initial concentration of the acid is represented as HA. For a base, it's flipped. We start with a base, we start with an anion, we react it with water, and then we get a conjugate acid. And so that's what shows up here. Okay, so that's the difference between these two equations. Now, what else are we going to say? Well, first of all, we said that pH is almost equal to pKa. So if this is true, then it must mean that this term must be almost equal to 0. Because if this is equal to 0, all we would have left is that pH is equal to pKa. That would also mean that this term here is about equal to 0 as we're making these assumptions and these approximations. So we're talking about this approximation and this one, and this is true if the log of the conjugate base over the initial concentration of the acid is equal to almost 0, or the log of the conjugate acid divided by the concentration of base is equal to almost 0. Okay? All right. So now let's move along. The way that we can assume this would mean that the concentration of the conjugate base must be about equal to the conjugate acid, or to the acid concentration. Because if these are equal, we're going to get this relationship to be equal to 1. So then that would mean that the log of conjugate acid over HA would be equal to the log of 1. And we know from our last exam that the log of 1 is equal to 0. So this is how we get to this. Okay? Similarly, over here, we're assuming that the conjugate acid is about similar to the base, the anion concentration, which would then mean that the log of HA over A minus is equal to the log of 1, which is then equal to 0. So this is how we get this, right? Okay. So that was just to digress and explain why we're assuming this to be equal to 0. So since that's the case, we then know that this indeed is true, and this indeed is true. So calculating pH can be calculated as the negative log of Ka, and pOH can be calculated as the negative log of Kb. Okay, great. So now that we understand all of that, we can go ahead and talk about making assumptions. Actually, there's still more I need to tell you. Okay, so point number 6. So let me keep rolling over here. So point number 6 still relates to approximations. So we're making approximations to solve for x and verifying that the assumption is valid. So we're making assumptions to solve for x. And when I say x, I'm referring to this x right here. Okay? And then we're using this, so the and, we're verifying that the assumption is valid. Okay, because remember, we were talking about before, the book was saying that if your percent dissociation was above 5%, you couldn't make the assumption that this x was going to go away when you solve for pKa, or when you use this equation saying that Ka is equal to x over 0.1 minus x. We're making the assumption that we can get rid of this x here and just say x squared over 0.1. So this is how this relates back. So we talked all about pKa and pH. In order to verify if this is valid, we're going to use something related to these arguments here, that pH is related to pKa and that we're related to x in some form or fashion. So we first are going to assume that because we have the pH being about equal to the pKa, that also means that the negative log of the H plus concentration is about equal to the negative log of Ka. So then let's take that a step further. We can then say that H plus is about the same as the Ka, and that the OH minus is about the same as the Kb. Okay, so now if we say that this is true, then we are saying that H plus is equal to x, which is equal to the Ka. Because remember over here in the ice table, x is equal to H plus. Now that we have a relationship for H plus being equal to Ka, because up here pH is about equal to pKa, and the negative, because of this down here, negative log of this is equal to this, we can then say this. So then we can say this. So if we're saying that x is equal to Ka, we can then use, for the percent dissociation, we can substitute Ka over HNO2. So we're saying that Ka over the initial concentration of acid times 100 is small. And if it's small, then the approximation is valid. Okay. So now let's go back. Is in problem 3, is this indeed true? Well, here's the easier way, like we said. If we want to verify if we can make this particular approximation by taking out this x, what we need to do is calculate this. So that means that we then we put the Ka over the concentration of acid, and we multiply by 100. And we see what that equals. So then we say the Ka here is given up here. That's 4.5 times 10 to the minus 5. 4.5 times 10 to the minus 5 divided by 0.1, because the initial concentration of weak acid is 0.1 times 100. And when we calculate that out, we get 0.45%. And that is super small. And since this is very small, we can then say that our approximation is valid. So we could go through and solve the way that we did. So we are eliminating this thought about the percent dissociation, and we're relating, instead of x plus being equal to, or h plus being equal to the actual x, we're saying that through this relationship here, that h plus is about equal to the Ka. And since that's true, we can put the Ka in for the H plus over the concentration of the initial concentration of acid times 100 to then get this value to show that this is really, really small. And since this is small, our approximation is valid.